All right. So we were discussing the conditions of the existence of Fourier series. Now we will continue with another interesting property of Fourier series, which is also known as the Gibbs phenomenon for discontinuities. The Gibbs phenomenon has been known by the scientists for a long time, but it was Gibbs who indicated that its existence does not disturb the convergence of the Fourier series coefficients. What's that? What does that mean? It means the following. Let me open a browser here to show you something from a link called mathsisfun.com, which was a link that I provided you with in Mergen. So you may already know it. It's explaining the Fourier series, but there's also a nice application online graphing tool which indicates something. So I will try to explain it on this particular web page. You may also take a look at all sorts of books for the explanation of what is a Gibbs phenomenon. First of all, it explains the fact that sine and cosine waves can make other periodic functions. So we add sinusoids at different frequencies and phases to come up with a combined new signal. So the question is, can we use sine waves to make a square wave? And we know that we could, and essentially we found the Fourier series coefficients of this particular example. We solved it already. We start with a sinusoid with the same period as the rectangular wave, and then we continue increasing additional term frequencies, but we decrease the magnitude of those. If you may remember, the magnitudes of the Fourier series coefficients were decreasing one by one. For example, the next odd thing, the next odd harmonic was sine 3x over 3, which was the odd harmonic, as you see. So when we add that to the fundamental sinusoid, as you see, we already start coming up with something that resembles a, of course it's not. So we add the fifth harmonic, sine 5x over 5, and we come up with even more accurate representation of a rectangular box. And we add more and more. Clearly, in the ideal case, we have to add infinitely many, because the Fourier series representation starts from k is equal to minus infinity and goes all the way up to k is plus infinity. So we increase and increase and increase. For example, when we come up with the 39th harmonic, it's almost a rectangular wave, but can you notice the ripples around the discontinuity points? It's like the horns, okay? Some ripples still exist. If you go up to 200th harmonic, those ripples start becoming smaller and smaller, but those horns still persist to exist. That persistence, I don't have a mouse, unfortunately, for this one, but you can see what's going on at 0 and pi positions of this rectangular shape. There are some small ripples or spikes. Those spikes never vanish. They become smaller and narrower, but their height is becoming still visible. That visibility of the spike at 0, at pi, etc., those spikes are called the Gibbs phenomenon. And they have some finite height, but their width will go to 0. So mathematically, if a function width goes to 0 and the height stays finite, it means that function does not exist because the energy of that function shrinks down to 0. Unfortunately, you can never observe it. You can never go that it's going away or vanishing completely for finitely many Fourier series harmonics. It happens only at infinity, which means it never happens. But its energy will be smaller and smaller and smaller, and but the spike will still stay there. That is called the Gibbs phenomenon. And mathematically speaking, there is no harm in it. It's okay. We don't care about that. Now, this particular web page has a Fourier series grapher link, as you see here. And it also gives you the formulas for finding the coefficients, but it's giving you the formulas in terms of cosines and sines. Because for applets, it's very difficult to deal with complex numbers. So instead of that, we come up with the real Fourier series representation, but not single coefficient, but two coefficients, one for the cosine, one for the sine. Nevertheless, this Fourier series grapher is a nice tool. So let's click on it and let's make some experiments with this one. This is a summation from 1 to 10 sine nx to 10. Sine nx over n from 1 to n from 1 to 10. So the first 10 coefficients of the Fourier series coefficients and the corresponding harmonics. This, by the way, is the Fourier series representation for a triangular waveform, but a sawtooth waveform, okay? It goes down and up and down and up. So it's like the sawtooth. And if you collect only 10 coefficients, you will get this. If you collect more than 10, let's make it 20. As you see, it's becoming more like the sawtooth shape, and the ripples are becoming more frequent. But do you notice the spike over there? That is the Gibbs phenomenon. Let's increase it to 50. You see, the spike still persists, but its width is becoming narrower and narrower. Let's make it 100. I think it doesn't run for 100. 99, let's make. I don't know, probably something like this. So the spike gets narrower, but it's still there. That is the Gibbs phenomenon. Let's click on the example button, which gives you another sawtooth, which is a shifted version of the previous one. So we will find the relation between the Fourier series coefficients of this sawtooth shape with the previous sawtooth shape. When we shift the signal, what happens to the Fourier series coefficients is a very good question. Another example, yeah, this is a good one because it's the rectangular box, but it's not centered around the origin, it's shifted. So we will see. Let's check the Gibbs phenomenon. Let's make it 80, for example. Look at that. It's really like a rectangular box, but the spikes are there and their energy is shrinking down to 0. There are, of course, other examples. This is also a rectangular box with some different fundamental periods or frequencies. This is, I think, sine. What are what's the corresponding thing? It may be an impulse, but the derivative of an impulse. This is not something that we are familiar with. Oh yeah, this is a good example of a situation where we don't observe a Gibbs phenomenon because there is no discontinuity. This is a triangular waveform, and the triangular waveform, as you see, is consisting of Fourier series coefficients. If you have only 3 Fourier series coefficients, as you see, it will be smoother in the not discontinuous, but not the non-differentiable position. But as soon as you go up to 10 or let's say 20, we can see that it is practically the same as the triangle. So it's very implementable by Fourier series expressions. It's very realizable. It converges very fast to a triangular waveform because there are no discontinuities. That is one of the reasons. And by the way, if you take a look at the formula, it is sine something over 2n minus 1 squared. Now, let me write it. It's like, I'm gonna erase it, but it's like sine something over 2n minus 1 squared. Now notice that these Fourier series coefficients shrink or become smaller in magnitude very quickly, more quickly than, let's say, sine something over 2n minus 1. Because as n goes to, becomes a large number or going to infinity, 2n minus 1 becomes larger and larger more quickly. So these are, in general, smaller than these, which means that the Fourier series coefficients quickly become zero-like. So they don't contribute to the Fourier series representation. The first few terms are large because the denominator values are not so large. Therefore, the Fourier series coefficients are still reasonably large. And quickly, those Fourier series coefficients become almost zero and they don't contribute to anything. And that's why we have a very fast convergence as opposed to the others where the denominator is not n squared, but it's like n. If the denominator is n cubed, if it is 2 to the power n, it's the denominator, then it means that it's very quickly converging to the original shape. That is something that we expect. All right. So those were the examples. I recommend that you take a look at the Fourier series exploration lab over there. This is this versus the other one. This converges faster because the Fourier series coefficients become smaller very, very quickly. Now, I want to open a new page and I want to list out something very critical. These are the properties of the Fourier series. We will see, we will do it all the time for all the other variants of the transformations. We will just explain the transformation first, give the formula for the transform and the inverse transform, and give some examples. But soon afterwards, I'm going to list the set of properties. And those properties are the ones that you're going to use for solving questions. It's indefinitely difficult to solve the questions using the formulas, using the transform formula or the inverse transform formula. It doesn't work that way in Signals and Systems courses. Instead, you have to use the formula. So it's like this. You will, let's come back to one of the examples. Let's reset, yeah. You will know the Fourier series coefficients of the rectangular box train centered around origin. And in order to find the Fourier series coefficients of this one, which is not centered around origin, it starts from 0, goes up, and goes down at the half cycle, etc. So what's the relation between the Fourier series coefficient of the one that you know and this one? You don't want to do all those integrations again to find the Fourier series coefficients of this signal. You don't want to do that. Instead, you want to use the properties. So what are they and why are they so critical? So these are the Fourier series properties. And these are the ones that you are going to use for solving questions. In a majority cases, 99% of the cases. So we have x of t, and I'm going to use this notation. Okay, take note of this. This is the notation that I'm going to use, a double arrow. And I will say that on it, I will say Fourier series, for example. So there is a Fourier series relation between x of t and, let's say, ak, okay? And I will also write a similar relation between y of t and, let's say, bk's, where t and omega 0 are common. So let's assume that the Fourier series, the periods of these two signals are common. Therefore, A1 corresponds to B1 in terms of harmonic frequencies. Then the first property is linearity. It means if you make or construct a z of t by combining x and y like this, then z of t will have a Fourier series coefficient or relation with, let's say, ck, which are the Fourier series coefficients of z, and that will be a times ak plus b times bk. So we combine the Fourier series coefficients. Okay. Excuse me. The chair is a little bit uncomfortable. So this is the combination of the signals will combine the Fourier series coefficients. But if the periods are not the same, you have to think very carefully which Fourier series coefficient harmonic index corresponds to which index. You can only combine if they correspond to the same frequency. Okay, if A1 is at omega 0 and B1 is also at omega 0, only then you can combine A1 and B1. So you have to first match the period or the frequencies for this linearity to apply. But it helps. For example, let me undo this. It helps you to solve some thought experiments, hypothetical questions for finding the Fourier series coefficients of this periodic signal. Like this. Why? Because this signal is equal to this signal plus this signal. Right? When you add the green and the blue signals, you get the red signal. So you find the Fourier series coefficients from here and say them AK, and from here you find BKs. And since the top red signal is the summation of the green and the blue signal, then the Fourier series coefficients of that red signal, let's call them CK, is equal to AK plus BK for all K. And because they have the same period, as you see, clearly, their periods are the same. So we don't find the Fourier series coefficients of this red signal, let's call it Z of t, using the formula. That would require a lot of integrals and some places where it is from minus t1 to minus t2, and then from minus t2 to t2, and from t2 to t1 again. So those integrals will be very difficult to handle. But instead of that, we are going to use this, and we will solve the question very easily. Okay, that was the first property. The second property, this was the one that I was mentioning about previously. What happens if you shift the signal. So we have y of t is equal to x of t minus t0. So x of t is shifted by t0, and x of t has Fourier series coefficients ak. So what are the Fourier series coefficients of y of t, which are bk's, in terms of ak's? It's not very difficult to come up with this expression or describe a proof of this. In fact, I am going to do it just for analytical exercising. Here, bk, which are the Fourier series coefficients of y, are equal to 1 over capital T integral within one period, y of t e to the minus j k omega 0 t dt. This is the formula of Fourier series coefficients, and that is equal to 1 over capital T within the same period, x of t minus t0 e to the minus j k omega 0 t dt. And now I will make a substitution of tau is equal to t minus t0, which would make t is equal to tau plus t0, and dt will be equal to d tau. Okay, these are the substitutions that I'm making. With these substitutions, that would be 1 over capital T. Now this integral, I'm still writing it within one period, but actually it is a shifted version of the same period, but the shifts don't matter. It's going to give you the same result. In fact, you can choose any kind of a period shift. Therefore, it's the same integral with similar limits, or even the same limit. X of tau e to the minus j k omega 0. Instead of t, I'm going to write tau plus t0 and d tau, which is equal to 1 over capital T over the period x of tau e to the minus j k omega 0 tau. Sorry about this. I'm trying to answer that. So it's not tau 0, it's tau. And e to the minus j k omega 0 t0 d tau. Now I will take this term out of the expression, and it's going to be e to the minus j k omega 0 t0 1 over capital T integral over a period x of tau e to the minus j k omega 0 tau d tau. And I'm going to say that this part is AK, because that's the Fourier series coefficient formula for x of t. So, in short, I come up with this final result. BK is equal to AK times e to the minus jk omega 0 t0. So if you shift the signal by t0, then it means you are multiplying the Fourier series coefficient by e to the minus jk omega 0 t0. Okay, it's like multiplying with a complex exponential. So this is one property that you have to remember or take into account. It may be listed, it will be listed in one of the cheating sheets that will be available to you. You will be able to print out, or you shouldn't use the computer screen for these things, for these formulas. So the formula sheet I'm going to dump on Canvas, Mergen, and you will have to print them and keep it like these pages with you during the examination, and you can always look at them. So this formula for shifting will also be available for you. You just have to know that this is the formula for that in order to solve practical numerical questions, example questions. All right, so this was property number 2. What is a property number 3? Excuse me. It's time reversal. These are easier properties. If y of t is equal to x of minus t, the flipped around version, what happens to the Fourier series coefficient? You can again solve for this one. You can say that y of t will be equal to, or let me start from x of t. Or I decided not to do it because it's quite obvious. If you just write the Fourier series expansion or the Fourier series coefficient formula, instead of y of t, you just put x of minus t and then make a relation or make a change of substitution of variables, saying that tau is equal to minus t. You will see that e to the minus jk omega 0 will be replaced by e to the plus jk omega 0, and that therefore the new k will be the negative of the old k, which means that the Fourier series coefficient of y of t, let's call it Fourier series coefficient, is bk, is going to be the Fourier series coefficient with a negative index, a minus k. So bk will be equal to a minus k. So if you flip around the signal, it also means that you flip around the Fourier series coefficients. Of course, as long as the signal is real. Otherwise, you will have to put a conjugation here as well. But let's forget about this for the time being. This much information will suffice for you. It will be sufficient for you. All right. Now, the time scaling is the fourth property, time scaling. So what happens if y of t is equal to a time-scaled version of x alpha times t? So you are multiplying t with an alpha. For the different values of alpha, it may correspond to an expansion or a widening of the signal, which changes the period. It increases the period or decreases the fundamental frequency, or it may shrink the signal, squeeze the signal to have a smaller period or a larger frequency, fundamental frequency. What happens to the Fourier series coefficients? It starts from here. X of alpha times t will have a Fourier series representation like this: ak e to the j k alpha times omega 0 times t. Normally, of course, alpha is multiplying t, okay, because it's x of alpha times t. So alpha was actually here, but I put it now here, and it looks like multiplying omega 0. And when I do that, I can say that this is alpha times omega 0 is, let's say, omega 0 prime or omega 1, a different fundamental frequency. And these AKs are the same. So the Fourier series coefficients of y of t, which are bk, are actually, and the Fourier series coefficients of x of t are, let's say, ak. These are the same. The Fourier series coefficients values do not change, but the corresponding fundamental frequency and k times that fundamental frequency, they change. So you have to draw the new Fourier series coefficients bk, sorry, bk, and I'm going to also draw ak's, which are the Fourier series coefficients of x of t. So this was a little bit incorrect. These are the Fourier series coefficients of x of t, okay? They are the same in value, but their locations are different. So I'm going to plot them on the same frequency axis, for example. bk, let's talk about b1, which was at omega 0, okay? The same a1, the same version of a1 will be here. So a1, actually I am putting it incorrectly. The red one was at omega 0, because a1 is the frequency of it is at the frequency of x of t, which was at omega 0. So I'm going to write it like this. This is omega 0, but this place here is alpha times omega 0. So we don't put the red ones, but we have to put the black ones. But their magnitudes or values are the same. They may be complex, they may be purely imaginary, their values are the same. B1 and A1 in value are the same, but they are at, one of them is at omega 0, the other one is at alpha times omega 0. If one of them is at 3 omega 0, the other one will be at 3 times alpha times omega 0. So the frequency axis is scaled, multiplied by alpha. So their positions are different. Okay. How can I write this? How can I put these in words? The Fourier series coefficient values are the same, but omega 0, it's not omega A, it's omega 0. Omega 0 is transformed into alpha times omega 0, a new frequency, okay? And k times omega 0 will be k times alpha times omega 0. So the frequency changes, but the Fourier series coefficients stay the same. It's like this. Think of a cosine omega 0 times t. What are the Fourier series coefficients? A1 is 1 over 2. A minus 1 is also 1 over 2. If you change omega 0, if you change the frequency, the Fourier series coefficients will still be 1 over 2 and 1 over 2 for A1 and A minus 1, but the corresponding positions of those Fourier series coefficients will be clearly different. That's what you have to know about this property. Okay, now let's proceed with the fifth property. Multiplication property. Let's say that z of t is equal to x of t times y of t. That's a strange thing. Of course, I'm assuming that x of t and y of t have the same period, have the same frequency, fundamental frequency. And x of t has Fourier series coefficients ak, y of t has Fourier series coefficients bk. So how can I express the Fourier series coefficients of z of t, which are ck's, in terms of ak and bk? And that is, this is a tad more difficult to achieve, a little bit time consideration. I'm going to just give result of this, because this result will continue to exist in other Fourier transforms, including the Fourier transform itself. And it will be so very well memorized by you that remember what we are talking about. L from infinite AL, K minus L, summation. Okay. Now, it may look a little bit different because it's in the subscript, but do you remember this formula? AL times B, K minus L summation for all L from minus infinity to infinity. Do you remember this formula? Many things. So I'm asking, convolution sum, exactly, Doğukan. That is very, very correct. It is the convolution of AK, convolution with BK. So if you multiply two signals with the same period, you convolve the corresponding Fourier series coefficients of those. A very interesting property. And this property will continue to exist. If you multiply two signals, their Fourier transforms are convolved. Their Fourier series coefficients are convolved. That is the property that you will always remember. And this is making the fundamentals of communication theory. Because in telecommunications, a very typical way to increase the frequency content of a low pass signal, like a speech signal, which is very much low band limited to 20 kilohertz only, we will multiply this signal with a very high frequency sinusoid. The high frequency are megahertz. And when you multiply with that kind of a sinusoid, actually their Fourier transforms will be convolved, and you will see what it really means in the frequency domain. We will come back to that one. But if you multiply in time domain, you convolve in the Fourier domain. Okay, that is the property that you will have to remember. The one before the last is the conjugate symmetry property. That's also very useful in several cases. If x of t has a Fourier series coefficient, then x conjugate of t, when you conjugate the signal, the Fourier series coefficients will become a minus k conjugate. Okay, which has a lot of implications. If x of t is real, is equal to x conjugate of t, isn't it? It's real. So a k is equal to a. You remember this? I was talking. I was telling you that. For example, a1 is 1 over 2. A minus 1 is the conjugate of 1 over 2, which is 1 over 2. If for a sine wave, a1 is 1 over 2j, then a minus 1 is the conjugate of it, which is minus 1 over 2j. That's why for real signals, the Fourier series coefficients centered at the origin are conjugate symmetric. But that conjugate symmetric is only applying to real signals, as you see. If x of t is not real, if it is complex, then you just have to evaluate these values. Okay, that's a good thing. But by the way, the conjugate and itself will have the same magnitude. If you're plotting the magnitudes of the Fourier series coefficients, you will see a complete symmetry for real signals. But of course, the right-hand side and the left-hand side versions will be just conjugates of one another. It has to be for real signals. The seventh and the last property that I want to talk about for today is so-called the Parseval's theorem. Parseval's theorem is the evaluation of the power of signals. Since these are periodic signals, we have to talk about power. Mainly, it's like this. You have a representation of a point along the black axis, and the total power corresponds to the length of this line. And when you rotate the axis, what happens? If you rotate the axis, that would correspond to the Fourier transform. This does not change by rotation. That's why such rotation form part of telling the power of the periodic the integral x of t squared dt over capital T. So this is the average power in time. Let me say it. Power in time is equal to the average power in frequency, and that is, since the Fourier series coefficients, I'm summing up the square or magnitude squares of the Fourier series coefficients. And see my having arriving late, so I'm waiting for it. Okay, so this is the average power in frequency. Now, what use can this Parseval's theorem be? There are proofs of this one, and the proof of Parseval's theorem starts from the generalized Parseval's theorem. It's very complicated in calculus. So for undergraduate students, that may be unnecessary. How can I use this? Let me ask you this question. What is the average power of a sinusoid? Of a cosine, let's say. Which is average power. Doğukan says that it's 0. It's the average value. The average power is different. As you see, I'm taking the magnitude squares. So the square of a cosine will not be positive and negative within one period. It will be positive and positive. And the area under it will definitely not going to be 0. It's not the DC value I'm asking for. It's the average power. So the example is, what is this cosine omega 0 t square dt with a 1 over capital T, which is actually 2 pi times omega 0. Sorry, omega 0 over 2 pi. You can also think of it like this, omega 0 over 2 pi within the same period. Magnitude cosine omega 0 t square dt. If you want to make it a simpler example, you may want to make it 1 over 2 pi from minus pi, or from 0 to 2 pi. From minus pi to pi is also valid. Come on. From 0 to 2 pi cosine t, let's say, square dt. What is this integral? It's a calculus question, and you may want to solve it. And you can do that. It's not very complicated. But if you know signals and systems, and if you know the Parseval's theorem, you can AK square, which is equal to, what is AK? There are two Fourier series coefficients. One of them is A1, the other one is A minus 1, and both of them are 1 over 2. We know it. So it is 1 over 2 squared plus 1 over 2 squared which is 1 over 4 plus 1 over 4, and that is 1 over, 1 over 2. It's 1 over 2. So this integral is equal to 1 over 2. How about that? Nice, isn't it? I found this ugly-looking integral and solved it very trivially, very easily, just using the Parseval's theorem. This Parseval's theorem, in practice, is beneficial if one of the domains is significantly easier than the other domain, because we know that the powers or the energies of the two parts of the time part and the frequency part, magnitude squared versions, are the same in values. So whichever is easier for you to evaluate, find the other using that one. For instance, we will in the near future, we will see that the Fourier transform of a sinc shape, which is sine x over x or sine t over t type thing, the Fourier transform of that one will be a rectangle. So what is the integral of sine square t over t square dt from minus infinity to infinity? It's a very difficult integral, but we know that the right-hand side of the equation is simply the square of a rectangle, which is also a rectangle. And the area under the rectangle is very easy to evaluate. You just multiply the height and the width, and that will give you the area. A very difficult integral becomes a very easy integral, okay? I am sorry to overshoot to 11 o'clock, but we started a little bit late. We chat a little bit, so sorry about that. If you have, you could have some other lectures starting at 11 o'clock, and I apologize for that. But I will stop at this point. Nevertheless, if you have any questions, feel free to ask, or you can collect your questions until Wednesday and ask them all together on Wednesday. Let's stop right now. It's already too long. And we will continue on Wednesday afternoon. Okay? See you then. Until then, take care. Bye-bye.